Right, hello everyone. So sorry I couldn't do this as a live class today. You all have heard enough about how I'm moving and have to pack everything up, but that's what I'm doing during the usual class time, is just firstly silencing my computer so it doesn't make noises. But I'm packing everything up right now. So for the last laboratory, you watched the video of the calibration of a pressure transducer in the axisymmetric jet. So this gave you an overview of what the actual experimental setup is, and then gave you an overview of how we collect those data, and it will be the same setup that you guys would have used to perform the actual experiment. So the key that we have, or the key stuff that we're trying to actually do in this experiment, is that we have some sort of pressurized jet, and it is exhausting into the room, into atmosphere. So we have this axisymmetric jet, and we're measuring things using a pitheostatic probe, which we can place at different locations in it. So if you were doing the real experiments, we would measure the diameter of the jet itself, and we would then place the probe at different streamwise locations. So we call this streamwise location X, and then we would be measuring at different streamwise locations, which we're going to non-dimensionalize by this distance here, d. So we then take positions at X on D, and I think, let me just look at the data that I've actually got, and hopefully you guys have all been sent. Yeah, we choose all the odd numbers up to 5, and we're actually going to include 0 as an odd number. It's not an odd number, but we'll include it. 0, 1, 3, and 5. So we take a set of measurements with the pitheostatic at the mouth of the jet, one at 1 diameter away, one at 3 diameters away, and one at 5 diameters away. And what we do during the actual data gathering is we then adjust the location in terms of Y. So the Y location is given a 0 at the center line of the jet, and we take measurements both above and below this, such that we're capturing the full profile in this jet. So say I'm here at X on D, X on D, not X equals D. X on D was equal to 5. We then take a series of measurements up here. So maybe one here, 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 here. Take a number of measurements, and at each of those we're recording the input voltage, the output voltage versus time to our pressure transducer. And because we've taken the calibration data, we can then convert those voltages into a gain, and then turn that gain into a pressure in pascals. So I'm going to have to pause for a minute because I realize this is completely out of battery. But we'll come back to looking at the calibration curve that you guys should have produced, and then we're going to work using those data that I'm going to show. Okay, and then I'm going to show you how we go through your own unique data and how we produce the plots that I'm expecting you guys to produce. So I'll be back in a moment. Okay, so I'm back until I've next got to charge this. So at each of these measurement points here, each cross, each of these would correspond to one set of measurements. Okay, so for each of those we need to know the X location along here, we need to know the Y location, and we need to know both the gain across, we need to know the gain, so we need to know the voltage across the input and the voltage across the output versus time. So those are the data that you guys have all got, you've all received, and then from each of those we need to turn it into a velocity measurement. So there's a couple of things that we need to do there. We've got a gain, so we need to turn it into a pressure, and then we need to use the Bernoulli equation to turn it into a velocity. Okay, so once we've got each of those, we then have a series of velocities, a velocity profile. We need to use the density of the air, and we then need to integrate along here to turn it into a mass flow. So what I'm expecting you guys to produce for this laboratory is 4 sets of these velocity profiles. One at X on D is equal to 0, one at X on D is 1, one at X on D is 3, and one at X on D is 5. So each of those is going to be a plot of the velocity versus the y location. And then from each of those as well, we're going to determine a mass flow rate, kilograms per second, and then we're going to plot the mass flow rate versus streamwise direction. So let's have a look at how we're going to do that. Let's think about all the things we need to do. So each of these data files, well, let's have a look at what these data files look like. So let's see what everyone has been given first. Let's go over here. I'm going to move my screen off. Each of you has been given a set of raw data files. Now this is just the way that I produce things. I've taken the original data and I've randomized them all using your student numbers as a seed for the random number generator. And that enables me to give you each unique data. So if the A number that I'm using here is your A number, doesn't mean you're special, doesn't mean that I don't like you or do like you. I've just picked a random number. So each of you has got a set of data files. You've got, I think, 46 data files that we've taken. We've then got file info and something called the 0. So let's have a look at each of these data files. Well, we can see here we've got a number at the start, raw data file, and then a number after it. So the numbers at the start are 0, 1, 3, and 5. So that's probably going to give you the indication that those data files correspond to the streamwise location at which those data were taken. Let's have a look at one of them. We see we have time, V in and V out, and I think we've got about 83,000 of these measurements in each of them. Yeah, 83,000. I think this was 1 second's worth of data taking at 83 kilohertz. So we've got a lot of data here for each one of them. We want to do this data reduction to take these big data files and turn them into a single number from each of them. So let's close that. In here also we've got a 0, and we're going to talk more about what that means. And then we've got this one, fileinfo.csv. Now this is the most useful one that we've got in here because it contains 3 columns. It tells you the D, which is the non-dimensionalized X or streamwise location. So this has an entry for each of the 46 files. It tells you where it was taken, which actually you can get from the file name as well. But it tells you here what the Y location is. So we've got X location, which has been non-dimensionalized by the number of diameters. We've then got the Y location, okay, and these are also non-dimensionalized by the diameter, so these are non-dimensional Y locations. And we've then got the file name of each of these. So it tells you which file contains which data taken at which point in here. So we're going to need to do some things with these data. Let's have a look at how we actually utilize the calibration that we created, because we need to do that for every data file. So remember that when we described calibration, we said calibration was a 2-step procedure. First step is for determining the relationship between a device's input and its output. And that's the bit that we've done. So we should have a plot that looks something like delta P, and then we've got the gain on here. So we've got a number of different measurements, and we've got a line of best fit going through here. Now your equation for your line of best fit should be something involving uncertainty, so we should have gain is equal to some really small number, let's call it m, plus or minus the uncertainty, delta p, plus or minus the intercept, which we'll call, let's say it's called g0, plus or minus delta g0. So we've got these should be really small numbers for us, and we're going to talk about what we actually do with those in a moment. And then actually these, we'll find we don't really need to use these numbers, okay? Because what we care about is we care about, for every increment that we've put in, how much does the output change? And that's what is given by these numbers here. So these are the slope, and this bit here, the offset or the 0, we'll talk more about that in a moment, The offset just tells us, well, what does the output actually give us when we've got a nominal 0 input? So if we were doing a real experiment, and I think you guys should have, I think I had this in the video, if we're doing a real experiment, you take a note of this number and you'd make sure that it doesn't change too much from day to day, because that gives you an indication, that your transducer is working correctly. But we don't actually use this number when we're interpreting the experimental data, because what's important is this one here. So let's say we've got this out. Now what you should find, and what I did find when I looked through the data, is that the uncertainty in our gain is about 2 orders of magnitude smaller than the actual sensitivity of the device. So I'm pretty happy with saying that we've performed a good calibration, and we actually don't need to worry about this number once we've produced it. As long as it's 2 orders of magnitude smaller than this, I'm happy with just using this here. So let's think about what this number actually means. This is then the sensitivity, and if I change the input differential pressure, it's how much the output changes. It's the rate of change of the gain with the differential pressure. Now what we actually want when we do the experiment, all of those data files, we can determine the gain and we want the differential pressure. So we take 1 over this number, multiply our gain by it, and that will give us the differential pressure. So this is what we determined during the calibration. Now I've just gone back through and redone my own calibration using the same data that you guys did. So let's just show you what I produced. Okay, so I produced a calibration image that looked like this. So this should be similar to what you guys have produced. You guys should have put X and Y labels on here, and I haven't done that. So let's put some on. PLT.X label. Okay, no, I've just done 2 X labels. That was not what I intended to do. I should have done a X label and a Y label. Okay, so I've got my input pressure in pascals, and I've got my differential pressure, and then I've got my output here. Okay, those numbers seem awfully high to me. Thinking about this now, let me just pause here and just check I've not done something stupid. Okay. Just gone back and redone my calibration. The error was annoyingly simple. I'd forgotten to turn my DHs from inches into meters. Okay, so everything was off by 1 over 0.0254. Okay, but I knew that was wrong, and I always try and tell you guys how I know when things are wrong is when I looked at this properly for the first time. My pressure was topping out at about 20 kilopascals, and I know that's around about 200 meters per second. And I know that jet doesn't go that fast. That jet maybe tops out at about 15 meters per second. Okay, so this is how I knew that was wrong. Redone my calibration. I've got this stuff here now. Okay, so I've got this new calibration number up here, and all of your data are made to use this graph here. Okay, so we're going to be using these calibration data. You could, if your number is close to this, feel free to use your number. I would rather that you used these numbers here to do the actual calibration. Sorry, not to do the calibration, to do the actual experiment. So this number here, we can see, as I said before, the error is at least 2 orders of magnitude below the actual sensitivity of this device. So we can use 1 over this number, which is 1 divided by 1.51680 times 10 to the minus 4, which gives us a calibration constant of C is equal to 6592.83, and the units for this are pascals, but remember I like to say it as pascals per volt, because this tells me we've got to multiply it by a gain to, sorry, really it's per volt I should put here. So we've got to multiply our gain by it to end up with a number. So we're going to use this number here, and this will enable us to turn our gains in each of those files into a proper pressure reading. And then from there we're going to use Bernoulli's equation to turn it into a velocity, and then we're going to integrate that to go into a mass flow. Okay, I'm probably today just going to get through the first step, which is turning it into a pressure, and then we're going to talk about turning it into, we can turn it into a velocity, and then the actual integration I might leave for next week for you guys. Okay, so let's have a look at these data. So I'm going to be working on this made up student number that I've got here. So I've got, we can see it's come from this file, make student data. I've got a set of data in here, and I've got my file info, which tells me which each file corresponds to. We're going to use this file here to tell us which file corresponds to which data, and then we're going to use this calibration constant to turn each of these files into a gain, which we do without this. And then once we've got that gain, we'll multiply that gain by this to give us the actual pressure measurement for that file. Cool, so we're going to go through that. So let me start a new Jupyter notebook. Let's go over here. I'm going to call it something suitable. So let's go in here. Let's start a new Jupyter notebook. I advise to always rename your notebooks when you open them. Call them something suitable. Don't call it that. Call it something that means something to you, okay? Because the number of files that I received that are called Untitled 7 or whatever, it's not good. So we're going to use some of the techniques that we've used over previous laboratories to help us bring these data in, and then we'll go through and show you guys how we actually import those data. So let's import some packages. Now we've used NumPy and Pandas, and we're going to use Matplotlib just to test those things, and we're going to import OS because it just helps us to parse things like file names. So import Pandas as PD, that helps us import files as data frames. Import NumPy as MP because that helps us do big operations on matrices. I'm going to import matplotlib.pyplot as PLT because I always do. And I'm going to import OS because that's useful. I'm also going to put this next line in here, which you don't need to do, but because I work with white on black, so I can sort of hide behind it like this, figures don't show up properly. So I'm going to just add this on here, plt.style.use, and the style that I'm going to use is dark background. But you guys don't need to do this, that's just for me, okay? We're going to include our calibration constant in this file. I don't advise hard coding numbers normally, but if we're doing a single experiment, that's fine to use. To include some constants, the calibration constant we said was 6.592.83. No, 6.592.83. I'm going to include the density of air, 1.225. And I'm going to include the diameter of the nozzle in meters, which you guys don't know, so I'm going to give it to you, 0.0325. Correcting my spelling there, I'm becoming more Americanized, I guess. So let's we'll pick where the data is, so we're going to say the folder that we're using. Now that folder that I was looking at, it's A20435113, which is just a random number I chose that was similar to your student numbers. 35113. Now you'd replace this with whatever your actual folder is. I know that you guys know how to do this, or most of you know how to do it, but I don't want to see, if I hadn't told you that, some students would come on the forum and say, I can't find this folder because you don't have it. So the very first thing we do with this experiment is we've got to work out what the 0 is, and I haven't really spoken about that. So let's talk about what that means. So this constant here tells us the sensitivity of the transducer. Okay, but we don't quite know how to relate that to an absolute value yet, because we don't know what the transducer thinks a 0 is on a particular day or in a particular setup. So let's talk about what that really means and how we interpret it and how we utilize that fact. And we all sort of know how to do this. There's probably something you guys have all done in the past. Say you're going on holiday and you've packed your suitcases and you're ready to go, but you're not certain if they're over the baggage allowance. Now, you could try putting it on your weighing scales at home in your bathroom, but you'll probably find that when you try and do that, they will obscure the screen. So I think, okay, I'm going to be a good engineer, I'll figure this out. What I'll do is I'll stand on it and I'll hold them, and then I'll step off and then I'll weigh myself. And I know I've got to subtract 77 kilos for my weight. That's what I weigh. Alternatively, you might be smart and you might think, okay, I'm going to step on it and then I'm going to 0 it. So it says 0 when I'm on it, and I pick them up, and then whatever my suitcases weigh is just the number that's displayed. That procedure that we sort of can intuitively work out how to do, where you might do it in cooking, you might put a water pan on the weighing scales and then determine a certain volume of water by pouring it in there and looking at the mass of water you've got. We all sort of know how to do it, but we also need to do it when we're doing experiments, and we need to sort of formalize this procedure. How's it going, love? I am recording, but I'm just going to I'll edit this out. Okay, I'm going to keep going for a bit, and then, okay? Okay, thank you, love. So the procedure for determining what a 0 is for an experiment is integral to every piece of data that you take. No, it is IE, isn't it? Every piece of data you take. So what we do in an experiment is, at the very start and at the very end of the experiment, is we take a measurement when we know the quantity that we're trying to measure should be 0. Do you mind just closing the door, love? Do you mind closing this door? I'm going that way. Okay. So for our experiment here, when the quantity of interest is 0, we're trying to measure this differential pressure. We would have the jet turned off. And we take a measurement, we again record the exact same things that we're going to be recording for each one of these data files, and we then look at what the output is from our system. And these recordings that we take are called zeros. The one that we take at the start is called the start zero. The one that we take at the end will be called the end zero. And you can take many of these to sort of check the repeatability. And for this experiment, in the data that I've given you guys 1, 0 to work with. That's the equivalent of knowing your weight or your mass when you stand on the scales, because you know you've got to subtract that number from everything that follows and every measurement you take, and that would then just give you the measurement that's in your suitcases. And you'll see here, I've said this value must be subtracted from every successive reading in order to ensure an accurate representation of the quantity of interest. And this is a case where I actually do mean accuracy, okay? Because this just will either move all of your results up or move all of your results down, depending upon the value of that zero that you've taken. And in doing so, it's ensuring that your results are in the right area, okay? And again, that example of taking it when you stand on the weighing scales to sort of measure your holiday suitcases, it might sound trite, but it genuinely sort of indicates what this whole procedure does. And I set up here that we take maybe one at the start and at the end. For this experiment, we've only taken one at the start. We're not going to bother with this end one because actually they aren't real data. But the reason why we do this is because any differences between the zero from the start to the end can indicate whether you've got an equipment failure. So sizable differences any sizable differences is called drift and can indicate more often than not, you will see some sort of drift in the zero of your equipment throughout an experiment. And more often than not, you'll see small drifts occurring because of things like thermal drift. Things heat up. Transducers are inherently electrical devices. With this current going through them during an experiment, they heat up, and you've got everything else in your experimental setup is also probably producing heat. Or maybe it's producing cooling, convective cooling by blowing air over your equipment. And in general, we know that all electrical devices change their resistance dependent upon heat. So you will see this occurring in a small amount, but any really large changes, and we're talking getting into bigger than 1 or 2%, that's something you want to observe and take account of. Because if you take your start zero and it gives you one value to subtract, and your end zero is very, very different, then it tells you that actually, I maybe subtracted the wrong value, or my equipment is changing and this is no longer valid throughout the experiment. Again, I'm giving you guys this bit as a bit of an aside so you can use it for the future. What we really need to know just for this experiment that we're doing, so you can earn your grade, is that we're taking 1, 0 at the start and we have to subtract it from everything else. So that's the very first thing we do. So we need to find that 0, work out what the value of the gain is, and then that tells us what we need to subtract from every successive value. So let's go back over to my Jupyter notebook. Let's have a look at the file info. This tells me which each of those files correspond to. Let's have a look at the rest of the files in here. We've got all those data files. and I've got my 0. This was the one taken at the beginning of the experiment, and we need to subtract that gain value from everything else. So we'll do that first. Let's grab that gain, and we will have a look at how we determine what the 0 gain is, and we'll subtract it from everything else. So determine the 0, this is what we need to subtract. So our 0 file is called, oh no, didn't mean to run that, 0.csv, comma separated value. So I want to import this 0 file, and I know that it's in this folder here. Okay, so rather than, I could write out my files equal to that's one way I could do this. That tells me that I can use both my folder name and my file name. This is a little bit clunky and doesn't always work if you switch between Windows and Mac because of the direction of the forward and backslash. So I use os.path.join, which is, we imported OS up here. It has an inbuilt thing that says, okay, am I on a Mac? Am I on a another Unix computer? Am I on a Windows computer? I know how to join files and directories and everything in all of those. So we're then going to import this. We're going to use pandas.readcsv, and I need to tell it to use this file in this folder. So I'm going to do my 0 data is equal to pandas.readcsv, and then I need to just tell it to take that folder and that folder and that file and put them together. So do os.path.join the folder and then 0 file, and then if this works I should have that 0 data. So we'll do print 0 data. Here we go. So I've got a pandas data frame with time, voltage in and voltage out. Okay, so I've got everything there, and I want to make a new column here that has the gain. So I need to take the output and divide it by the input here. To 0 data, I'm going to make a new column called gain, and I'm going to use pandas to take, sorry, I'm going to use Jupyter to take this column divided by this one. Sorry, using NumPy rather. NumPy.divide, I can hear it when I say things wrong, sorry. NumPy.divide, I'm going to take 0 data, the outs, and I want to divide it by 0 data, the in. And that should produce a, no, it doesn't like it because I put a quote after it. Let's do that. There we go. So I've now got my gain here. That's the gain when I've nominally got nothing going across my transducer. We can see that we still have a gain that's of the order of 5 to the minus 4. Okay, or 5 to the of the order of 1 to the minus 4, I should say, because this is 5 to the minus 5. So we're now going to take the average of this column, and that's going to give me the value of the mean gain that I must subtract from every other value. So mean gain is equal to 0 data. The mean of that. Okay, let's move that line feed down. And again, it's important that we do this with the gain and not the output, because this tells us what the 0 of the gain is. And then if we change the supply voltage or the excitation at any point during this experiment, this is still a valid 0 that we must remove, as long as we're doing it in terms of each of these gains. So we now want to know what the X on D locations that we were looking at. So let's import the list of files. So let's say this was step 1, determine the 0. We now want to work out, import the file list. Step 2. So let's work out the data files that we have. Now that's in this file fileinfo.csv. So we're going to load this in, and I'm going to just import it as a pandas data frame again. Exactly the same syntax as before. I've not made any typos. There we go. We now have this in as a pandas data frame, so I can use this to work out what we've got in here. Now I know that I've got streamwise locations of 0, 1, 3, and 5. I can also just confirm that by extracting it from this file info. So I'm going to say x on d's is equal to, I want all of the unique values within this column here. So I'm going to put file info d dot unique. Just check this works because I'm doing this all off the cuff. Yeah, I've now got 0, 1, 3, 5 here, so that's useful for us. So remember, we want to go through, and the way that we're going to go through this is we want to go through all of the zeros, work out the gain, put it to a pressure, put it to a velocity, and plot it. We're going to do that today. Okay? We then need to do all the ones, do the same, put it to a gain, put it to a velocity, and plot it. Same with 3, same with 5. So we're going to do all of that today, and then in the next video that's coming out, I'll show you how to turn that into a mass flow rate. So we've now got each of those. Step 3 is then to loop through each of these. So we're going to say for each XD within this XD thing that we've got, a list, yeah, it's a list. We're then going to say that the files that we have are equal to the elements of that file info data frame that we've got, where it's got the D location is equal to this X on D. And let's talk through what I actually mean by that. So what this is iterating on, this is iterating on 0, 1, 3, and 5. So it just goes through this, goes for every item within the X on Ds, and then just changes the value to 0, 1, 3, and 5. And this enables us to separate out those streamwise locations. So let's just have a printout of this file info again. Let's just show us what it looks like. So I now want to go through, and when I've got the 0, I want to say pick all of the items with a 0 here, and we're going to do something with them. When I've got the 1, pick all the items with a 1 here, and we're going to do something with them. So we use a little bit of Boolean logic here, and we'll say that these files are equal to file info, and I want to know file info where the D column is, which is this one. Every item of file info where file info is equal to XD. I'm just going to do another print after here to separate these out. So there we go. So what it's done each time is the first time it's gone through, it's printed out these ones, just printed out the rows corresponding to 0. And then I've put a line feed in. Second time it's printed out the rows corresponding to 1. But importantly, it's kept these column headings, and that's what's really useful about using pandas. Cool, so we've got that there. Let's go through, and I can just see my mic is looking like it's a little bit quiet. I'm just going to pause and just check my output is actually coming out before I have to re-record this whole thing. I'll be back. No, everything was good. The number of times I've had to re-record lectures because of a faulty mic, I am now very alert for that happening. But we've now been able to extract, and we've gone through this loop 4 times, and each time we're just selecting a different batch of files that we're going to process. And for each of these, we have the Y on D location, which is the vertical location of that pitot probe within the stream. And then we're now going to process these somehow. So let's think about how we can process them. So I'm going to make a new data frame to collect the data at that location. Let's think about all the things that we need to collect. So I want to get through these, and I want to turn it into the Y location, and I want to have the gain, the change in pressure, the velocity, and the change in velocity. Sorry, the uncertainty rather. Let me just have a look at this 1 second. Here we go. So we're going to make a new data frame. Things that we want to have in here are the gain, plus or minus the uncertainty in the gain. We want to have the pressure, plus or minus the uncertainty in the pressure, which comes directly from the uncertainty in the gain. Because we've got the calibration constant for that, so we have that. And the other things that we want to turn that into are going to be velocity, plus or minus change in velocity, and eventually we're going to want to turn it into the mass flow rate here as well, but we're not going to do that just yet, okay, because this would then, we actually need to take all of these. So we're going to have these values, so the gain, the pressure, and the velocity for each one of these files here, okay? So I'm going to make a new data frame for it. The columns I want to have in here, we input these as a list. The columns need to be y on d, which is just going to be taken directly from here. And then with each one of these, I need to take gain, the uncertainty in the gain. I then want to have the pressure, the uncertainty in the pressure, and then I want to have the velocity and the uncertainty in the velocity base from those. So we're going to go through and do that for each of them. Okay, so if I run this, nothing seems to have changed because I've produced this empty data frame for each of them, but I haven't done anything with it yet. So let's go through, and I'm going to say determine the gain from each of these data. The first step is actually, I've sort of jumped ahead a step there. So let's just say we just want to look at this first location. So I'm going to say we're only going to look at the first element in here just to cut down on the amount of processing that we do. Let's do a print of these files. Let's print this. Oh, it doesn't like that. That's fine. Let's just do a print of these files. Okay. So each time I've got this here, I now need to remember I'm iterating 4 times through. I'm getting this is on my first iteration. This is my second iteration. This is my third iteration. That's my 4th iteration, or times through that loop. So what I want to do is then the first time through, I want to then loop through each of these files, do some processing, and then put them into this data frame that I've just created. So let's do that. I'm going to say for f in all data, and it's called file name. Let's just check this works. No, it doesn't work because it's not called file name in all. Oh, sorry, I shouldn't be looping through all data. All data is the one I just created. I should be looping through these files. Yeah, so it's now telling me that the first time I go through here, I get all of these data. So every time I go through, I now actually want to load these data up. So I'm going to say loading the data corresponding to this current file. So we'll say this data, which is just the one that we're currently working on, is going to be a pandas.read CSV os.path.join, and then I need to tell the 2 things, which is the folder. The folder we called this folder, and then the thing that I want to give it is that f, which is just that iterable, or the current value of this. So the first time it'll be this one, second time in that one, and so on. If I run this, doesn't like it because this folder is not, oh, it's called the folder, that's why. Okay, so down here it said name error, this folder is not defined, and it's because I called it this folder here rather than the folder. So let's run this again. And it's gone through, and this is probably going to take a little while. Oh no, it's run through and it's imported all of them. That doesn't take a tremendously large amount of time, which is good. So we can now determine the mean gain of this file. So when we did this before, we used this line 28 0 data up here. So I'm going to copy this line down here, and I'm just going to replace 0 data with this data, which now means that I've got this column that represents the gain. And if I was to print this out, you'll see that each of these, now there's going to be lots of these printed out, now has a gain column in each of them as well. Okay, I don't need to do the printing out because I know that it's there. So let's get rid of this, and we now want to say the actual gain. We now, from each of these, we need to subtract that 0 that we actually had before. So I'm going to say everything in here we want to subtract this one from it. Okay, mean gain. So rather than calling this mean gain, let's call this gain 0 up here. So line 22. I'm going to go down here and I'm going to say this data I need to subtract that gain 0 from. You can't see annoyingly because it's gone off the edge of the screen, so let's do, oh, didn't want to do that. Let's put a line feed in here. Okay, so this line I'm saying for each of this data, the gain is equal to the output divided by the input with that value subtracted from it that we determined. There we go. So now each of those has got a corrected gain within them. Let's just do a quick, and I think something might happen here if I subtract this 0. So let's just try it. Print. Yes. Okay, so I wanted to just check, because we're subtracting data and we're just subtracting this 0, some of the early files where we've got nominally 0, because we're taking really low pressure readings, we're actually going to get negative values here. And that's not something that can physically be realistic. So what I'm going to do with each of these is I'm going to take any value that's less than 0, I'm then going to convert it to just being equal to 0. So we'll say this data G, so we'll say this data, where this data G less than 0 is equal to 0. Now we're going to try doing the same again. Yeah, and it's now just replaced those negative values with 0. So what this is doing is saying within this data, which is that data frame we've got, pick the values where the gain is less than 0 and then set those to be equal to 0 instead. Okay, that's just because I've done this exercise before and I know what can happen if we don't get it right. So we now want to record this value, the mean of this value, into this all data one that we've got here. Okay. Let's think about how I'm going to do this. I haven't done this properly yet, so we'll do it at the end. We'll do this at the end. Okay, I'm going to put them into a dictionary and then put it into this data frame here. So we're now going to get the mean gain now. So that gives us the mean gain of this data file. We can then turn this into the pressure difference by just multiplying it by that calibration constant, which we included right up here. We then want to look at the uncertainty in this as well. I'm going to do the same as taking the mean, but I'm going to replace this with the standard deviation, and that's going to give me the uncertainty of those data. We then want to do the same with the uncertainty of the differential pressure. I'm going to make the assumption that actually I can just take the standard deviation of the gain and multiply it by the calibration constant as well. And that's going to assume that most of the uncertainty comes from this standard deviation here. And again, I know that this is a much larger source of uncertainty than the calibration constant itself. So this is suitable to do at this point. Okay, so if I run this, I don't get any errors, which means I haven't made any problems here. So we've got the gain, and we've got the pressure. We've now got the uncertainty of both the gain and the pressure. We don't actually necessarily need this one here, but we certainly need this one. We need to turn this into a velocity as well. So we know that the delta P that we've got is effectively what's called the impact pressure, and it has to be equal to the dynamic pressure at this point. So it's equal to a half rho v squared. So if we want to get the velocity is equal to the square root of 2 delta P on rho. So rho is 1.225, because that's the density of air at atmosphere, and then delta P is the thing that we've just got here. Okay? And again, because the delta P, the uncertainty in this is a lot larger than the uncertainty in the density here, we can just assume that the uncertainty in the velocity is equal to the uncertainty in the velocity put through this same equation here. And then to get the uncertainty, dV is equal to 2 times ddP times rho. So we've got everything that we need to do. We've got now, so we've got the, let's go back, we've got the gain plus or minus the uncertainty in the gain, the same with the pressure, the same with the velocity here now. So we need to take each of these and we're going to put them each into a dictionary, and then we're going to put that into the all data frame up here. Okay, how do I get the only thing I can't think how to get now is that Y location. So let's figure out how we get this. This is going to be interesting because we're iterating on these files, file name. I've got no means of getting that Y location out. So the easier way to do this is I'm going to say for F and YD in these files, file name. And then I want to turn this into a zip, so I'm iterating on two things. And the second thing I want to iterate on is, let's just have a look at these files. I've got this column YD, so I can just get this number out. These files YD. Let's just check if I can get that into here. Nope, doesn't like it. Key error YD. So that key, it's Y underscore D with a lowercase d. That's why. So it says down. I've gone all the way through. The error is normally at the bottom of a big bunch of error messages. It says key error, which tells me I've tried to access something in the data frame by a column that doesn't exist. So I've called it Y underscore D with a capital, but it's called Y underscore D with a lowercase. So let's go down and change this to go up and change this to D here. I'm just going to remove this cell so it doesn't skip to the bottom when I run this. There we go. So I've now managed to get the YD within the same loop. So we've got all of these things. We want to tie each of these up to a certain value of YD, and then we want to put all of those values into this new data frame that I've created called all data, which is just for that one axial location. So let's go through here and just think about how I can do this. I'm going to make a dictionary of all of these data. this dict, and we'll say we've got to use the same keys as I had up here. Okay, so I'm going to pick these keys out. Just going to put these here, and I'm going to copy them in. So I've got y_d, and the value for y_d, which is, this is a key here, needs to be the value that I've pulled in, y_d. Okay, I need to have the gain, or the mean value of the gain needs to be the mean gain, which I've called mean gain. I then need to have dg, which I've called dgain. Okay, so that dgain comes from up here. I then need to have p, which is the, it's called p, this is really delta p, but we'll just call it p for the moment. That's going to be this one up here, which is the differential pressure dp. The uncertainty in that dp, which again is d delta p really, should be ddp, which is just the value I've got from before. Let's check this is still printing. Yep, I'm going to put a line feed in here so you guys can read everything I'm doing. And then I need to have velocity and the uncertainty in velocity. So the key of velocity, I actually called this, with the key is v, I called this variable v up here as well. And I need to do dv here. To run that, cool, it produces a dictionary. So basically this is then just a row of that data frame that I want to populate up here. I now need to put this in there. So I'm going to say, append this into there. So I'll say put all data is equal to all data dot append. And the bit that I want to put in is this dict. And I want to ignore the index, because indexes are the sort of row numbers. I don't want to have them. So I'm going to say ignore. I think it's called ignore index. Yeah, ignore index. I just did a tab autocomplete is true there. And then I'm going to come out of the loop and I'm going to do print all data. Oh, there we go. Now, it might have seemed a bit abstract the way I was going about this, but I wanted to show you why this is useful using data frames, because I've then got, for this first streamwise location, I've got my YD locations, I've got the gain, uncertainty in the gain, pressure, uncertainty in the pressure, velocity, and uncertainty in the velocity, and that's really, really useful. So I now can go through and do the plotting. So let's just see how we can do that. So we've got now, you might think I have to make a matplotlib plot at each of these, and we do have to do that. Fortunately, we've got all this data into a pandas data frame. Now, it may seem like I just did that to confuse you and make things more complicated, but some of the methods that pandas data frame have enable us to do plots directly from this graph, sorry, from the data frame. So I'm going to say, let's do all data dot plot. So all data is just this data frame, but it also has this method plot, which enables us to do a matplotlib plot from this. So I'm going to do a scatter, and the things that I want to plot are velocity versus YD. All right, so let me have a think about this. Yes. Yes, my velocity wants to be the x, and then I want YD to be the, yeah, that's fine, that makes sense. And then I'm going to just include my dv as my x errors, because I don't have an error associated with my y location. So these bits in here correspond to the keys that I put into this row and are in this total data frame. So let's just remind ourselves, let's just print this out again. So this all data is a data frame, and this is now enabling me to plot. What I'm doing here is I'm saying plot on my x-axis, I want this column velocity, and on my y-axis, I want this column, the y location. And the errors are going to be taken from this dv column here. that looks pretty graph-like to me. Very happy with that. Okay, so what we can see here, we've got, let's include some labels on here. Let's do some labels on here. Let's do a title first. The X location I've got given up here, it's called X on D. Okay, so we've got this, we've got the exit velocity profile. We see on here, we've got the location away from the center line. We've got a very flat velocity profile here. We've actually got a reduction in the center. We've got the error bars here. We see we've got a nice, pretty uniform jet at the exit. Here we've got a slightly more normal shape distribution at x on d is equal to 1. X on d is equal to 3. We've still got reasonably fast velocity in the center line, but we've got this much smoother curve now as this mixing is occurring in the jet. And then this last one, we see this jet gradually smoothing out at x on d is equal to 5. Now, this is a pretty cool way of making plots. This is a lot that I've just given you today, okay? So, excuse me, this is where I expect you to be at by the end of the first week. I'm not going to ask you to hand it in though at this point, because I want you to go further and work out the mass flow rate. So I want you guys to be at this point by Monday Monday the 3rd of May. I'd like you to be at this point by, okay? Because you'll be receiving your next video that tells you how to determine the mass flow rates based upon these. And I'm not going to be available to answer questions in that last week, so please, please, please get this done this week. Okay, hopefully that's a lot of interesting and useful things for you. If you've not worked with pandas data frames too much before, you can see why they are useful means to capture data, because they enable us to quickly do operations between columns and then to do and record plots based upon those columns as well. If there are any questions, you guys know where to find me. I look forward to going through this with you, and I look forward to the next step of this. Once again, I'm sorry that I wasn't available to be here for a live lecture this week. We'll have a review towards the end of the week to make sure that everyone's up to speed on this method. I hope everyone's having a wonderful week. Have a great remainder of your work week and a good weekend, and I'll see you soon. Take care.